Okay, so today we're gonna discuss about the mechanical property and behaviors of, especially for metal and alloys. Okay, so those issues to address are what is a stress and strain, and what they and why are they used instead of load and deformation, and what is elastic behavior? What's the definition of elastic and the plastic deformation? And what's the difference between them, and what's the mechanical behavior, okay, between the elastic and the plastic behavior, and what are the toughness and ductilities? So what's the performance? What's the mechanical performance that can define the toughness and the ductility? Okay, so those issues will be discussed in these chapters, and we are only discuss about the isotropic materials. Okay, we only discuss about isotropic materials. So for metal, some mechanical properties that we have to know, we can do this called the tensile test. That means we can have a rod or plate, metal or alloys spaceman, okay, and we can put it out to tell fracture. Okay, we can do this called the tensile test. Okay, we can define a gauge length, and it could be an initial length, can be defined as the initial length of the metal samples, and after a fracted, it will measure the its cross section, okay, its cross section and the length after fracture, okay, after fracture. So we can know its elongation and its area reduction rate, right? And from those results, we can figure out whether these metals are ductile or brittle or no. So there are lots of mechanical properties can be figured out from the tensile test. Okay, from the tensile test. Okay, so first let's look at the elastic deformation. What's the definition of elastic deformation? It's when we have okay, that's temporarily forget about the atomic structure. Okay, let's look at the macroscopic point of view. When we have a metal rod and on top is fixed, it's here is fixed. Okay, it's clamped. Okay, it's a boundary condition, right? So before applying a load, the atomic arrangement is fixed, right? Right? It's fixed. And when we apply a force at the end, one end of the sample, and this metal rod must be extended, right? So the length must be elongated, right? Certain volume. And that's mean the bonds between atoms are stretched, right? The bonds between atoms are stretched, right? Compare the initial case, right? Must be stretched. And after we release the load and the length change will return to its original dimension. Okay, so when we apply a load, if we apply this force versus the length change, we find out the relation between the force and the length change is linear elastic. Okay, and the slope is a constant. Slope is a constant. When the force is released, okay, and the length return, okay, when we load it, when we apply the force, right? We apply force and the length will be elongated. When we release the force and the length change will return. Okay, and the slope between the force and the length change is a constant. It's a constant. And therefore, elastic means reversible. This behavior is defined as the elastic deformation. That means the external force released, the length change will return to its original case, to its initial case. Okay. Okay. So what is the plastic deformation? Okay, what's the plastic formation? The same if we fix a metal rod, right? We clamp it. Okay, we clamp the metal rod, fix at one end, and we apply a force. And the force is large enough to trigger the slip process occur. Okay, this means the metal atoms will slip along this closed packed plane, right? We already mentioned in previous chapters, right? So the metal will be the metal will slip along this slip plane and the closed packed plane, right? Of course, the bonds between the plane and atoms are stretched. Okay. So when the as we already mentioned previously that the when the slip process occur, that's mean what? That's mean the plastic deformation, right? That means that it's plastic deformation. So when the force applied is large enough to trigger the slip process occur, and it is plastic deformation. That means permanent. Okay, so when the force is released and the length change will not return to its initial length, right? And the length change remain called plastic. Okay, plastic deformation. So from the force versus the length change, what's its behavior? So when the force is within the elastic range, that means the force, the relation between force and length change is elastic behavior, right? It's elastic behavior. That means when the force is released, the length will return, and when the force is large, higher than certain value, so and this plastic deformation occurs, right? The plastic deformation will dominate this behavior. That means the slip process occur. Okay, therefore the relation between force and the length change is not linear. Okay, it's not linear. Okay, it's not linear. And when the force is released, the length change will return to certain value. Okay, will return to certain value, but not its initial length. Okay, therefore the length will return. Okay, the length will return. Okay, will return, but we will not return to its original length, right? And this length change is plastic deformation. Okay, it's plastic deformation. Okay. Okay, so we already mentioned that when the slip process occur and the plastic deformation forms, right? So, and the plastic formation causes by the shear force inside the spaceman. Okay, the shear force. Okay, So this is the shear force along this closed pack plane. As a review some previous chapter. Okay, or we say it's a slip plan or slip plan. Okay. Okay, so let's look at the. We already mentioned that. Let's combine this elastic and the plastic deformation. We can combine it. Okay, so when the force is below a certain value, after the force released, the length change will return, right? Therefore, we just, if this applied force is within certain value, we can say, okay, this material always has this elastic deformation or elastic behavior. Okay, no matter how large force or how large stress we apply on it, if the stress is lower than certain value, okay, we can regard it is elastic behavior. That's meaning after the stress release or the force release, its length change will return to its original or its initial length, right? That's meaning in this region, okay, in this region, okay, in this region. However, when the force or stress is higher than certain value, that means the plastic deformation or the plastic deformation occur, right? And when this deformation reaches to this point, and after the force or stress are released, the lens will not return to its initial case, right? Will not initial case, okay? And this line will parallel to this linear elastic region, okay? Parallel, and this distance that we call the plastic deformation or plastic strand, okay? Plastic strand. Okay. And we can define some mechanical properties from this tensile test. Okay, from this tensile test. The first is called the yield stress. Okay, sigma y. Stress at which noticeable plastic deformation has occurred. Okay, and this stress is defined as the yielding stress. It's as the yielding stress. So when we apply a tensile stress, right, to stretch a metal or alloy rod or plate, so we can plot the stress versus strain curve, right? Right, so we can plot this stress and strain curve like this. Okay, and we can take the offset about 0.2% of the strain, and we plot a parallel line to the elastic region, so they are parallel, right? And we find out intercept. Okay, we can just estimate offset of the strain is about 0.2%, and we plot the parallel line to the elastic region, and we can find out the intercept here, and we can define this point as the yielding stress. Okay, yielding stress. Okay. Okay, so what the mechanical property can be found from this stress and strain curve? Stress and strain. Yeah, what's the what are the mechanical properties can be find out from the stress and strain curve when we do the tensile test. Okay, one is called the Young's modulus or modulus of elasticity. Okay, which is the slope, of the elastic behavior between stress and strain. Okay, so you can think of this way. If we have a higher slope, if this after this test and this alloy has a higher Young's modulus than the others, so what's this mean? What's the meaning of its mechanical behavior? Right? So from those tests, from the tensile test, you can figure out lots of parameters, mechanical parameters, and you can figure out a lot of mechanical properties of a specific metal or alloy after running this tensile test. Okay. So the higher slope of the stress and strain curve means that maybe it's more brittle, right? It's more brittle, and its hardness is higher than the others, right? Okay, higher than the others. Okay, so just that you know, the slope of the stress and strain curve in the elastic region is called modulus of elasticity or Young's modulus. Okay, Young's modulus. Okay. And we have to define some materials which has no linear region. Okay, some specific materials which has no linear regions. So we can define its secant modulus or tangent modulus. Okay, it depends on how you specify your product. For example, if we have a product and we run this tensile test, well, although it's not, there's no elastic region for that materials or for that product. However, we have to define its modulus for our specific product, right? So we can define it. Using the secant modulus or the tangent modulus. Okay, secant modulus or tangent modulus. And these two modulus are not the same. Okay, if these two modulus are not equal, means that this material is nonlinear. Okay, it's nonlinear. Okay, it's nonlinear. Okay. So we already introduced what is the definition of stress and what's the definition of strain is. So I have to mention this again. Let's have a briefly retrospect what we already taught before. So the tensile test, definition of the tensile test is the applied force normal to the original area before loading. Okay, and the shear stress is the shear force parallel to the area before loading. Okay, therefore, if a product or if a sample withstand a certain force, right? With a certain force such like this, right? So we can just split this force into normal and shear. Okay, we can split this force into normal and shear, right? And the shear may be in this direction, right? Or this direction, or this direction. Okay, and more details for this stress and strain issue will be introduced in your course called the materials mechanics. Okay, materials mechanics. So probably skip some issues of this materials mechanics here. Okay, so let's define parameters called the strength. So what is strength? Strength is the length change divided by its initial length. Okay. So after tensile test, the space must be stretched, right? And the length must change, right? Elongated, right? And this length change divided by the initial length that can be defined as the tensile strength, right? Generally, when the specimen withstand apply a tensile force, it must have the tensile strength and the lateral strength, right? In the tensile direction, this specimen must be stretched and elongated. However, in this lateral direction, right, its lateral dimension must be shrinked, right? Right? Therefore, this lateral strength is minus, right? It's minus. And remember that the strength is always dimensionless, okay? It's always dimensionless, okay? And how to define the shear strength? Shear strength. We already mentioned that the shear strength is that the shear force parallel to the area before loading, right? So this is the shear force, and this is the plane, and this is a parallel. These two are parallel, right? And when apply a shear force, right? This spaceman must be deformed, and we define the shear strength as the delta x divided by y. Okay, define the shear strength is the delta x divided by y. Okay, that means it's tangent theta, right? It's tangent theta. Okay, it's tangent theta. Therefore, tangent theta is shear strength. It's a shear strength. Okay. Okay, some components must withstand some specific force or stress applied. Okay, for example, for the cable, it's kind of a cable for ski lift. So when you see a cable component in a machine, you must realize that this cable must withstand a simple tension. Okay, simple, but not compression, but not shear, only tension. Okay, and of course, for a machine, for a component or for mechanical parts, that must withstand multiple forces applied on it, right? Of course, tension is the simplest one. Okay, so maybe some component withstand like torsion or shear or compression simultaneously, right? Okay, so what is the tension? Like draft shaft. So when we have a rod or shaft, right? And we have the couple moment applied on it. So when we look at this small element on the surface, shaft surface, okay, it can figure out the shear force applied to parallel to its element. Okay, parallel to its element. Okay, parallel to the area, the smooth area in that element. Okay, therefore we can define the shear stress, right? Driven by torsion, okay? Okay, for more details of this torsion, the Sam will be introducing the materials mechanics course, okay? And how about this element, this member? What kind of force or stress applied on it? And if you guys have already learned this statics, you must know this type of member is called a two-force member. Two-force member. So what's the characteristic of two-force member? Okay, so usually for a structure, the two-force member is always withstand a simple tension, and in this case, it's a bridge. So this two-force member is withstand a compression, right? Compression, stress on it. Okay, you have to remember this. Okay. And what's this? It's a pressure tank. It's a pressurized tank, right? So what it will be inside it? So here it mentioned is air, right? It's air, or maybe not only for air. It could be liquid. Okay, can be liquid. So if we look at the shell on this pressurized tank, this shell, right? It's a smaller piece of shell. So you can figure out it's it's called a biaxial tension, right? Biaxial tension on it, on this small element on the shell. Okay. Of course, if you were a fish or if you were a goldfish, you will feel what kind of force or what kind of stress on your whole body. And this stress is called the hydrostatic compression. If you are a fish, okay, you will feel the hydrostatic compression. Okay. Okay, so let's look at the behavior of the tensile test. So running the tensile test for metal or alloy, what kind of mechanical properties we can figure out? I already mentioned that the slope within this elastic region is called the Young's modulus, right? Young's modulus E. And the proportional region, we can figure out a point is called the proportional limit. We call it the this is called the proportional limit. So beyond this proportional limit, what's going to happen? That means a certain plastic deformation occur, right? Certain plastic deformation occur, and we define a strength. It's 0.2%, right? And we plot a parallel line with the elastic region, and we can figure out a point. It's called the yield stress, right? Yield stress. Okay, so we always use this stress as the fundamental of mechanical design. Okay, mechanical design. So below this is elastic, and beyond this is plastic. Okay, and some other metals or alloys like carbon steels will find two yield points. One is called upper and lower. And during this lower yielding stress, you can find out that the yielding stress remains. However, the strength keep growing, right? Okay, so well, it will happen in the sheet manufacturing, and there's a phenomenon called the Luger's band. Okay, if some spaceman have this kind of stress and strain curve, you will know, oh, wow, this kind of, it must have the lunar span phenomena when you just stretch the metal sheet, when you stretch the metal sheet. Okay, that means certain points, a certain part of this metal already yield and other parts still not. Okay, so that's mean it's kind of a specimen. We have a different, different color. Okay, different color on this metal sheet. Okay, so let's compare the Young's modulus versus the temperature. So if we compare with three different metals, tungsten, steel, and aluminum, so what does figure tell us? What does figure tells us? It tells us the tungsten has the most stable Young's modulus corresponding to the temperature change, right? And aluminum as the highest variation between the Young's modulus and the temperature. So what's this tell us? So you can tell which type of materials can be used in high temperature application, right? High temperature application. Also, it's also indicates that the modulus, Young's modulus, or modulus of elasticity is correlated to what? Is correlated to melting point, right? Of course, tungsten has the highest melting point compared with that of steel and aluminum, right? Right. You can see for the tungsten, it has the most stable Young's modulus with respect to a temperature, right? Okay, so let's look into the detail of the tensile test for metals or alloys. Okay, initially when we pull a metal rod or plate, its cross section will remain the same. Okay, so when we start to run this tensile test for the metal, its cross section keep remaining. Okay, its cross section keeps remaining, and we keep stretch it, and this specimen is stretched and elongated, right? And its cross section still remains. Okay, still remain and keep still remain. And when the stress reach certain value, it's called ultimate tensile stress. Okay, it's called ultimate tensile stress, the highest value of the stress. Okay, and after the stress is higher than this point, UTS, a mechanical behavior occurred. It's a geometric change. It's called necking, right? And the force, when the stress higher than the UTS, this metal start to necking. Okay, so if you keep putting, okay, and this metal rod will fracture. Okay, finally, you will fracture, just broken. Okay, just broken. Okay, and of course we can define its Young's modulus with the 0.2% offset and its unit stress. Okay, and its unit stress, and we already know the slope in the a linear region or elastic region is Young's modulus or modulus of elasticity. Is that clear? Okay, so we already introduced the stress and strain, right? The engineering stress. That's mean the force divided by the area before loading, divided by the area of cross-section before loading. And engineering strength means the length change divided by the original length. Okay. Okay, so let's look at one mechanical phenomena. I already mentioned this proportional limit, right? It's totally linear relation between stress and strain. And as the load increases, the specimen becomes non-linear elastic deformation at the stress, called the proportional limit, right? So if we apply stress within this proportional limit, right, within this point, so its elongation will return, right? Well, its elongation will return to its original length. And when we apply a stress, a load keep increasing, displacement will become nonlinear elastic deformation. Okay, so when the force or stress beyond this point, right, and below this yielding stress, below the yielding stress, for example, maybe I just so if we have this 0.2% offset, right? 0.2% offset, for example, we have this offset here. So this point is the yielding stress, right? And within this range, we call it nonlinear elastic, right? This is nonlinear and elastic. That means its elongation will return to its original dimension. Okay. Okay. So let's look at this figure when we apply a tensile stress, right? For example, if this stress is beyond the yielding stress, and we release the load, right? This elongation will return to certain value. Of course, this permanent deformation created, and we apply stress again, right? Apply stress again, and we can release it again, right? And we can apply the force again. Okay, so what this behavior, what kind of a mechanical behavior you find out? So you figure out the yielding stress, right? The yielding stress is strengthened, right? It's strengthened. Okay, it's strengthened. So what's the reason why the yielding stress increase when we loaded, unloaded? What kind of the mechanism to strengthen the yielding stress? Well, it's called the dislocation, right? As we keep loaded and unloaded, we keep change, right? Its dimension. That means the dislocation density increased inside the displacement, right? We have the higher number of dislocation. That means the displacement is strengthened. Okay, it's strengthened. Okay, of course, it will become more brittle. Okay, it will become more brittle. Okay. Okay, so let's look at the other mechanical parameters. Is called the Poisson ratio, or the other mechanical properties is called the Poisson ratio. Okay, so what is Poisson ratio? So when we have the tensile test or compression test, the dimension change, the lateral strength divided by the tensile strength or compression strength as the Poisson ratio. Okay, is the Poisson ratio. Okay, therefore the slope between the tensile test, the tensile strength and the lateral strength. Okay, tensile strength and the lateral strength, and the slope between them is the Poisson ratio. Okay, it's the Poisson ratio. Of course, for this compression, it's the same. Okay, it's the same. And usually for metal, its Poisson ratio is about 0.3. For ceramics, its Poisson ratio is about 0.25, and for polymer, it's about 0.4. Okay, so what's the mechanical behavior thus with different Poisson ratios? Okay, so let's look at this. If we apply a tensile stress, right, and in the tensile directions that must be increased, right? Usually, generally, when you apply a tensile stress, the specimen's length must increase. However, in its lateral direction, the dimension should be shrinked, right? Should be reduced, right? Should be reduced, right? Therefore, we define the Poisson ratio as this trend in x direction, right? Or y direction divided by z direction. Okay, divided by z direction. Right? The minus sign means that we have to modify the Poisson ratio value to be positive. Okay, to be positive. Okay, to be positive. Okay, and usually the Poisson ratio will be between 0 and 0.5. We're within this range. Okay, usually. Okay, so what kind of a mechanical phenomena if the Poisson ratio is minus? Can you explain that? What kind of mechanical behavior could be if its Poisson ratio is minus? So you can think of these questions. Okay. So as I already mentioned, that if you apply a tensile stress, right, its dimension will be stretched in the tensile direction, and the dimension will be reduced in its lateral direction, right? And in this case, its Poisson ratio is positive. So what kind of a mechanical behavior if the Poisson ratio is negative, right? So when we apply a tensile stress, if its lateral direction you're expanded, you're increased, and the increase rate is higher than the tensile direction, that's mean the material's Poisson ratio is minus. Okay, it's minus. Okay, it's for the rod, or it's the same as that. It's a rectangular specimen. Okay. So, questions. What kind of materials whose Poisson ratio equals to 0, and what is application? And what kind of materials whose Poisson ratio equals to 0.5, and what is the applications? Right, you can think of these questions. And if we plot, as already mentioned, that the Young's modulus is the slope of the elastic region, right? Elastic region in the stress and strain curve. Okay, if we plot the force versus separation between atoms or whatever, between atoms or particles, right? So we can figure out the slope of the force corresponding to distance. The higher slope, that's mean the stronger bonding between two particles. That's mean we need a higher force to separate these two atoms or two particles. Okay, therefore the slope of stress-strain curve depends on the bond strengths of metals. Right. So for this force, the figure of force versus separation, the higher slope indicates that it has the stronger bonding between atoms. Okay. And there are some other elastic properties. So as I already mentioned, the torsion, right? When we apply a torsion of a shaft, and there must be a angle, twisting angle, okay? When we apply this moment or this torsion, okay? And when this moment or torsion released, and this angle will return to zero, right? So we can figure out the relation between the shear and the shear strength. And the slope in this linear shear and shear strength plot is called the shear modulus. Okay, shear modulus. So you can think of this way. The shear modulus means that this materials, if we have a higher shear modulus, means that this material has the high resistance to torsion. Okay. And the other the parameter is called the elastic bulk modulus. That's mean the material's resistance to compression. Okay, if we measure this, for example, this hydrostatic compression, we plot this relation between this compression versus the volume change rate. That means the volume change divided by its original volume, right? And we can figure out the slope within this linear relation, right? And that can be defined as the K bulk modulus, and that is the resistance to compression. Okay, to compression. And the spatial relations between this modulus for isotropic materials are this. Okay. However, you have to remember that it's only for isotropic materials. Okay, and those modulus and the mechanical properties are the shear modulus, Young's modulus, and the Poisson ratio, and what? Bulk modulus. In the bulk modulus, okay, you have these relations, but you must be reminded that in these relations are only for isotropic materials. Okay, only for isotropic materials. Okay, so we're gonna stop the course here, and we'll continue this chapter maybe next week. Okay. So let's see you next week.